growth and ceiling. Oh, such a lie. Dr. Joe, we were hitting the other day. We were batting live. And another girl in my class hit a change up so hard. It went into like, it broke the light that was inside the cage. Like it dented the metal that was on top, and the metal hit the light, and everything just shattered onto the ground. It was awful.
That's hilarious.
And we decided that
all right, how's it going?
Joe, it's going kind of shitty. I don't agree with Haley's writing. So.
Yeah, we're aware. You got up early to come take my test.
Exactly, that's why I'm trying.
I get that.
You got up early to take the linear algebra test?
Well, he made us take it at 8.
Wow, that's just.
He made you take it at 8?
No, it was an option.
Or just.
It's true, it was an option. You could have come in at 9 and tried to do the 2-hour test in an hour.
What'd you do? Feel good?
All right.
Got your Lady Gaga in here?
How'd the video go?
Pretty good.
Oh.
I watched it.
There was a lot.
How long is it? I'll watch
Was
it
that
right
a
now.
lot of letters?
Like
Yeah.
hats, and I was like, okay, I was like,
There's letters and hats and everything else, yes.
I'll watch it
making
right
sure
now.
I wrote it correctly.
Oh, that's all right.
All right. So the whole point of that is, the reason why I did that, I don't expect you to remember that formula because the formula is not fun. But the whole idea of that is that there are different ways to construct confidence intervals depending on what parameter that you're trying to estimate with the interval. Okay? The reason why we didn't do it for means, just to show you quickly, if we try to do the same concept as popped up in the video, for means, remember, we're looking for the difference between the mean, the sample mean and the population mean being less than or equal to some value to be equal to one minus alpha. That was how we started everything, right? And all we did was just make an interval based on rewriting the absolute value state and moving some things around, correct? One of the reasons why we could do that is because we only have the mu in one spot. We noticed last time when we did that for population parameters, the p was in 2 spots. So really we didn't put the p by itself in the middle, right? We had the p in the middle, but we also had p on the outsides because of the variance. But then we said we could estimate the p with the p hat to get an estimate for the standard deviation piece, right? We did that last time. We don't really have a similar problem here because of we kind of do because we have to estimate the standard deviation, the population with the sample standard deviation. But we don't see the mu, is what I'm saying is I don't see the mu in both sides, or in all 3 spots of any double inequality, like we do for the population proportion, right? Population proportion is definitely in all 3 spots. Okay. Now, but if we attack this in the same way that I did in the video, remember in the video, basically squared both sides and moved everything to one side and called that a quadratic function, right? If you do that here, you would have x bar minus mu squared and then minus z sub alpha over 2 times sigma squared over n. So clear the fraction, square both sides, and subtract. Is how you would get that. Just like in the video. Okay. Just different ideas. And then just like in the video, let's multiply this out. You'd have a mu squared. You would have a 2x bar mu and x bar squared. And then this term straggling on the end.
You did all this in the video, right?
I didn't do any of this in the video. I did it for the population parameter in the video.
So this for the mean?
Yeah. I want to show why we didn't do what I did in the video earlier. That's the whole point of this.
New question. Do I need to write? Like, do I need to know this? Like, yesterday you went through something that you didn't need to know.
Is it going to be on the test? No. Is that what you're asking me?
Is it going to be on homework?
Is this going to be on the homework? This won't be on the homework. The final answer for the confidence interval that's in the video will be on the homework.
Is that long equation?
Just to plug in numbers into that equation, yes. I mean, you're literally going to take that formula and plug some numbers in.
It's okay. If I can't figure it out, it's
You're going to come ask me anyway.
I mean, it's my problem. It's also your problem.
Yeah. All right. Anyway, so the same idea as in the video. I want to know where this is equal to 0. It's a quadratic in mu. So what if you're using the quadratic formula? What's A? What's B? And what's C? 1, negative 2x bar, and this whole thing is C, right? Because we're solving for mu. So we would have 2x bar plus or minus the square root of 4x bar squared minus 4 times 1 times that thing. Oops, I keep forgetting my squared on here. That z should have a squared on it because I squared both sides and then forgot to write it down. Okay. All right. That was a quadratic formula. All right. So both terms have a 4 in the under the square root. If I factor it out and take the square root, you get 2. I got a 2 in the front and a 2 on this and a 2 on bottom.
Oh my gosh,
they all cancel. Yep. So this 2, this 4, this 4, this 2 will all go away.
What about the x bars?
Okay. What about the x bars squareds?
You can pull them out and then square root it and then have an x bar.
This is a minus sign. But something else happens.
Can you split it? The x bar cancels out under the...
I think they go away, don't they?
Oh yeah, okay.
You got an x squared and a minus x. I got an x bar squared and a minus x bar squared. Those go away too, right?
Yeah.
We got a minus and a minus.
Plus.
That'll be plus. And I can just do the square root of this thing, can't I?
Yes.
Yeah.
Yep. So when we're done, this becomes x bar plus or minus z alpha over 2 times sigma over square root of n. Aren't those?
I've ever seen that.
Yeah, I don't think you've ever seen that before, ever. Notice you end up with in this case, you end up with the same endpoints of the confidence intervals that we came up with before anyway. Yeah. So this is why we didn't bother going through this method before. It doesn't give us a different thing. However, for population parameters, it gave us a different thing. Okay.
So like for different
For different parameters that you're trying to estimate, you might get different ways to compute the confidence intervals. Yeah, that's exactly right.
Why would you do that?
It depends on what the size of the sample is. That's when you get a bigger difference for the one that we did in class last time and the one that was on the video. The smaller the sample size, the more different those two will be. In the video, I pointed out that the larger the sample size is, the smaller certain fractions you get, and then you just end up with the same confidence interval, essentially. So for large samples, it really doesn't matter. Okay. Now we are going to talk about a third one. The third one's not that big of a deal. Okay. So this is more for if your P, and in particular your P hat, is small. So if your P is small, say you are trying to do sampling for a rare genetic disorder. Well, the probability that you find someone with a rare genetic disorder is pretty small. If you're trying to estimate what the percentage is that of the population that has this rare genetic disorder, you're going to have a hard time getting an estimate just based on the fact that it's going to be a hard time finding these people, right? In fact, you might get samples where you get nobody, right? And if your p hat is 0, then your estimate for the standard deviation piece is going to be 0, and you're going to get no confidence interval, right? Okay. So there are cases when the p is small that using either of the two confidence intervals, either the one we talked about in class or the one that's on the video, aren't going to be very useful. Okay. So one of the ways to do this is the author says it's been suggested by a couple of other people that we use a different estimator, and that estimator is what the book uses as a p tilde. What it does is it makes sure that you don't get 0, essentially. So this p tilde is going to be y plus 2 over n plus 4.
What's y?
Y is the number of successes. Right. So this guarantees that you're going to get some shift off of being very, very, very small. Even if you get no successes, you're still going to get some proportion here to be able to calculate a confidence interval. Yeah. It also works the other way around. If the probability is very, very, very high, so you expect to get almost as many successes as you do as your sample size, if the probability of success is really, really high, this also shifts your denominator so that you make sure that it's not 1 at the other end, which would also give you a standard deviation of 0 in the confidence interval. Yeah, Grace.
Why a 2 and a 4? Is there any specific reason, or is it just like
Probably, let's see, I don't know if it says in the book. My guess is that the 2 and the 4, oh, no, wait. If you look at off the video, this is where the 2 and the 4 come from. If we look off the video in that first part, I got to write down, make sure I have pieces correct. That part there. If I multiply everything by n, this will be, this p hat, of course, is y over n, because that's your sample proportion. So you get y plus that, and then n plus,
That's so we divided by 2.
oops, yes, thank you. I want it divided by 2. It better be. I want it divided by 2. Okay, so those two things are equal to each other, right? Without a doubt. What's the most common alpha value that we've seen as we're doing these confidence intervals?
5.
Yeah, 5%, right? 0.05. What is z sub alpha over 2 when alpha is 0.05?
6.455.
That's
1.96.
it's the 1.96 when it's alpha over 2, right? What's 1.96? What integer is 1.96 close to? 2. What do those numbers turn out to be?
2. Oh,
2
2
and
squared is
4.
4.
Yeah.
2 divided by 2. Got it.
Yeah.
Forgot to square.
So you get 2 and 4. That's where those things come from.
Oh, it was being
All right.
again.
So, anyway, if you use this, and one of the homework problem asks you to do this, if you use this one, you use the same form for your endpoints for your confidence interval, by the way.
So when would we use this instead of p hat? It still looks like a p hat.
It does. We use this if you've got a very, very small number of successes compared to the size of your sample, or if you have a very, very, very large number of successes compared to the size of your sample. Like if you got, say, 1 out of 10,000 or 9,999 out of 10,000, you would do this to adjust.
Adjust for what?
The fact that this piece is going to be really, really close to 0 in those cases.
It will be pretty obvious from the problem.
Well, especially since it tells you.
It'll tell you.
It says, the problem that specifically that I assigned says use the first formula, use the second formula, use the third formula.
Wait, they're numbered?
Yeah, but not first, second, third. It's use formula 6.5-1, use formula 6.5-2, use formula 6.5-5, or whatever the numbers were. But the problem literally says use this one, use this one.
It's pretty obvious.
Michael, do you want to play?
She wanted it spelled out.
All right. Are we okay with that as far as why we might want to use such a thing? Again, if your regular p is really, really, really small, and you're multiplying it by something else that's less than 1, and then dividing it by something, you're getting this to be really, really close to 0. If it's really, really close to 0, you're not getting much of an interval at all. So in those cases, you might want to make an adjustment like so, and then recalculate, just to give you a little bit more of a range of values that's more likely to contain. That's the idea behind it, the true value. Remember, again, we're just trying to get an estimate for what the actual population parameter is. Does that make sense? They also go through and talk about doing confidence intervals for differences. Remember your confidence interval for your difference of means? What did it look like? Large sample, not small sample.
X bar.
It was X bar. It was like an X1 bar and an X2 bar, right? And then what went under the square root?
This variance of 1.
Yeah, the variance, and then.
Over. I was going to say n, so that's okay.
Oh, I'll make an n, sure. I think the book uses n.
The next one.
Yeah, the next one's m, yeah.
Yeah.
If for a large sample, that's true, right?
Yep.
Yes,
Okay.
sir.
Those are our endpoints. Yeah. Is your service die?
I haven't had
Oh,
you what?
the pen died. That causes a problem.
Battery?
Yeah.
Yeah. How do you charge it?
You don't. It has a battery.
Did you make this when you connect it to your computer like you have now to charge it?
That would be kind of cool if they made it just.
That would be amazing.
That would be awesome.
I would really enjoy that.
All right. So, how would these change it?
Looks like they
How do you think these individual pieces would change if you did population proportion, a difference in proportions?
Why do we not have the means about those views?
Because I forgot it. Thanks. I do need that Bart.
X to the one.
Oh, yeah.
What?
I didn't match him. I was trying to hurry to get the next part. I'm sorry.
It's okay, Dr. Joe. It's okay. As long as we get a pizza party at the end.
So is that
Well, of course you're going to get a pizza party at the end. Why wouldn't you?
What we do?
Yeah, why wouldn't you?
Because Michael is being mean also as
Well, Michael might not get any pizza, but everybody else will.
Ready, Dr. Joe? I'm not ready.
Oh, I better stand up if I want to catch.
What's that? Oh,
Sure.
sideline.
Just
All right. So how would this change if we had population proportion versus, or how do you think this would change if we had population proportions versus differences of means? What do you think I would replace the X1 bar with? Yeah, P1 hat and
Why is it?
P2 hat. But I'm looking for a difference of proportions rather than a difference of means.
Can you remind me again with the proportion? Number of successes.
Yeah. And then what do we replace the variance piece with, do you think?
Y's and M's.
Can we use p hats in it?
Sure.
The square root of p hat times 1 minus p hat is a plus p2 hat times 1 minus p2 hat over m.
Yeah. It just follows the same form as what we did for difference. If we're doing population proportions, we probably are going to have a large sample size. Most likely. Yeah, Morgan.
so the p hat times 1 minus p hat, is that, so that is the sample variance for p hat?
Mm-hmm.
Okay.
Yep.
And then is that formula above for the means, is that the same when we have the pool variance, or that's just for small?
That's for small. Yeah. It's okay?
Wait, when would we use this one?
If you're doing difference of proportions.
Yeah, but I'm kind of.
All right. So let's go on to the next section, which talks about I think it says estimating samples. No, it says sample size. All right. So in a lot of different polling things that you see, you'll see that they state whatever the values are for the proportion, and then they'll say margin of error plus or minus 3 percentage points, or plus or minus 5 percentage points, or what have you, right? So we're going to talk about how do you know you've got that margin of error. Okay. So we're going to do this for means and do this for population proportion using the first formula that we came up with. So for your mean, your one sample, just estimating a population mean, one population mean. Our endpoints for our interval look like this, right? And for population proportion, they look like this. Now, I purposely did not put hats on the second piece of this. I wanted it as just a P. And I'll talk about why here in a second. Now, it'll probably be longer than a second.
Does anybody have a running equation? Should we start?
We are given dynamic class. Pretty much like all of this.
Yeah, but this is really more detail.
This is a what?
Really more detail. You're telling me stat the same level of intensity?
No,
as the rest?
I'm not saying that. I'm just saying.
Okay.
It's pretty.
So when you're looking at that margin of error, the plus or minus whatever parts, it's really talking about trying to get a handle on this piece of your confidence interval and making that within a certain range. So when it says margin, so when you see a poll for maybe registered voters who plan to vote Democrat in the next election, when you see that percentage posted and then it says margin of error plus or minus how many percentage points, that value they're giving you is the p hat. The plus or minus piece is this part. Okay. Now, basically what you're doing is you're basing this part on how large of a sample do you need. You're picking the sample so that you know how large the sample needs to be to get that small, based on a certain confidence level. So let's do a problem and see what we need to do this. So let's look at 6.6-2. 6.6-2 says that we know that X is distributed normally, unknown mean, but somehow we magically know the variance. Okay. This is what sample size do we need to estimate, or I'll just write it this way, estimate mu to within 1.5 with 95% confidence. I said estimate to within 1.5. The problem actually says the maximum error of the estimate is 1.5. the maximum error of the estimate. That's the language is in the problem. It's margin of error.
Okay.
Yeah, maximum error of the estimate. We're trying to make, remember we use these symmetric confidence intervals, right? We're putting the value in the middle and going left or right of it the same amount. That's a symmetric confidence interval. Okay? We want the left-right amount to be at most 1.5. We want it to actually equal 1.5 in this case. How big does n have to be to get 1.5 out? So all this means is that we need to solve an equation. That's the error part, right? The left-right part. So all we need to do is solve this equation. We're given the various pieces, right? What's the z sub alpha over 2?
1.96.
Yeah, 1.96, right? We just mentioned that one a little bit ago, correct? Because alpha is 0.05.
Yeah.
Z sub alpha over 2 is going to be the 1.96.
Yeah. There's just-
What's sigma? 13? And equals 1.5, is that something you can solve for n?
I'm not sure that's still.
Okay.
My algebra skills are a little.
Morgan.
So
Are we actually doing?
so the p hat, is that included in the margin of error? Or just the z?
It's just the piece, not the front piece. Just the piece that's after the plus minus for both of them
Is the margin of error?
is the margin of error. Yeah.
Okay, so then are we?
It's how far you're going left or right from that point estimate. How far your interval goes from the point estimate, left or right.
Okay. So then the number we get out there or the 1.5, is that like the end of your interval? So it's like,
It's 1.5 away from the point estimate.
oh,
You're allowing yourself to be 1.5 above or 1.5 below.
I see. Okay.
Well, that was not right. I just got was not even close.
Yeah, what?
I got 288, but it doesn't work.
288.
Is that what you got, too?
Yeah.
Why? Maybe.
Now, as a technical point with these, you should always round up. No matter what the decimal is, you should always round up. Yeah. Why should I always round up?
Round up to what?
Yeah, you want to make sure that you have that margin of error. You can't have a partial of a sample, right?
289.
So you should always round up no matter what. Because you have to have a whole number of things that you sample.
What if you sample a person that has no legs?
I don't. That's an awful statement, but
What does that have to do with anything?
There's still a person, Grace. You jerk. You're an awful person.
I'm not sure what that had to do with anything.
That is fun.
she
Alright.
was just trying to make a point of saying, like, if you have a sample of people and you have like 288,
A partial of a person? Yeah.
so that's half.
So
a
she's
person.
it was half a person?
That was fun. It might have been a little dark, but.
It was funny. All right. So let's do another one here. So let's say that, let's look at 6.6.5. Yep, that's the one. We've got a 98% confidence interval in this case that they want. They...
Is this all we're doing?
Hmm?
Is this like all you do for this?
Yeah.
Does it get harder?
No. No, they really don't. We're going to do one for proportion here in a minute. We want to estimate mu to within 0.25. We have a preliminary sample size of, I don't know why they even bother saying that. We don't need that part. preliminary sample. We have an X bar is 35.68 and an S is 1.723. What sample size is needed? Ooh, hey. I know I didn't write out the whole problem, but
Is that the whole problem?
that's the pieces of the problem that we need.
That's probably all you did.
Yeah. They tell you a piece of superfluous information in the problem. They tell you the preliminary sample had 32 items in it, but it really doesn't tell you much.
That probably was.
All right. So notice what we're not given in this problem that we were given the previous problem. Previous problem, they told us what the population variance was, right? So in this problem, they don't tell us what the population variance is. So, which means we don't know the population or the standard deviation. All we have to work off of is the sample standard deviation, which is why they tell us we have a preliminary sample given to us. Okay. It's telling us that we're going to have to use this information to do our estimate. Right? But it's the same idea. We still want to set the z sub alpha over 2 times sigma over square root of n equal to, what's the margin of error they want this in this case? 0.25. All right. This value, the z sub alpha over 2, we have to get from the table or from Excel, either one. I go.
So it's 3, come on.
It's 3? You can use 3 if you want. I think it's 2.33.
There's a 3 in it.
I think it's probably 2.32. Oops, sorry, I lied. Where is it? 2.01. 2.326. That's what it is.
So what's the alpha over 2 they're using?
Yep. And then we'll have to use the estimate that we have for the standard deviation, so the 1.723. Don't have any other thing we can use. It's the only information we're given. And if you solve that for n, what do you get?
Traces on the case.
256.986. So 257.
Okay, so that would be the sample size that you would need to get to that. You can always double check the answer here too. Hey, look at that, 257. Definitely enough, we did it right. All right. Not that I didn't trust Grace's calculations.
I wouldn't.
All right. So the second part asks, is the sample size reasonable? Okay, so keep in mind this is not polling. This is actually trying to estimate a mean of something. Now I'm going to go to the context of the problem. The problem is testing the mean strength of the left hinge on a vanity cover molded by a machine. Okay. It's trying to test the strength of a hinge. If you're testing the strength of the hinge, what do you have to do to the hinge? You have to break it. Good, exactly. You have to break it. Is it reasonable to break 257 hinges? Depends. I suppose it depends on how expensive the hinges are, right? If it costs you a penny to make the hinge, breaking 257 of them is not that big of a deal. If it costs you $50 to make a hinge, you probably don't want to break 250 of them.
I wouldn't break any.
You wouldn't break any? Just trust it.
I am broke.
You are broke. So you have to make a decision. They want this precision on the strength of the hinge, but to get this precision, they have to test that many hinges. Do they really want to do that?
No.
Well, it's a business decision at that point, right?
Like,
think about it from cars.
yeah, I was
Right?
say that. It's like-
You want to smash the heck out of 250 cars to test something. That sounds fun, yeah.
What if they're toy cars?
It depends on what kind of car they are, right? You go take a smart car, go smash the heck out of it. You know, take some Porsches, you probably don't want to.
Well, the smart cars are kind of expensive too.
Yeah, but those would be really fun to smash because I hate those things.
I don't know why people want to drive with their death traps.
Yeah, they look like death traps, that's for sure.
They're so easy to park.
I'm sure.
The one good thing that comes out of this, it's so easy to park now.
Yeah, that was amusing.
Like, because in cities they have like these car rent, like you can literally like you just park there. You can go up like seriously, just take the car.
All right. You would do a similar thing for your population proportion. The one thing that you might look at, so the population proportion equation that we would always want to solve is this one.
Would this all be the same if we were using the T distribution?
Yeah, but
Does it exist?
well, your T distribution, once you get above 30, you go to the normal anyway.
Yeah, but let's say that we're not above 30.
Then you would still do the same thing with the T. You would just use a T value.
That's what I'm saying.
Yeah, do the same thing. The chances that you would get a small enough margin of error to matter and not be off the T table is pretty small. I don't think anybody would do it for a T table.
Are we doing it in our homework?
No.
It's not. If we're not going to use it in the real world,
Why would you use in the homework? Yeah. All right. Especially if you're just doing calculations. All right. So this is again, this is always dependent on your confidence level, whatever it happens to be, right? This you're choosing as well. You choose your confidence level, you're choosing your margin of error, whatever you happen to want it to be. So the one thing you have to estimate is the P. But here's the good news with the P. You really don't need to estimate the P and still be able to do this margin of error business. You can use an estimate for the P, but if I just think about this numerator and not anything else in the formula, just this numerator, what kind of function is that? It's a quadratic. Which way does it open, up or down? Down, right? Because it's got a negative P squared, right? So its vertex would be its maximum value, the maximum you could possibly get. Where does it cross the x-axis if I were graphing it as a parabola?
One. I guess, to be clear, I didn't actually. By your face, I'm guessing I'm wrong.
You want to know why you're guessing?
Oh,
It's
zero,
factored.
0 and
0 and 1. Where does the vertex of a parabola happen with relation to its x-intercepts?
in the middle.
In the middle. So where does the maximum occur?
0.5.
0.5. So what's the biggest the numerator can actually get in that fraction?
0.5.
Well, the P can get, the biggest the P can get is 0.5. What's the biggest the numerator can get? 0.25. So absolutely no matter what, the biggest this can ever get is 0.25, no matter what the population is. Period. So you can always use 0.25 here for your margin of error. All it does is maybe you have to pick a few more people to talk to.
Yeah, but then we're gonna get our answer wrong on the homework.
But if you have social anxiety, then you don't want to talk to people.
So you probably shouldn't be a pollster. You should probably pick another line of work.
Why would anyone ever want to be a pollster?
They're really committed to being involved in politics and with their cause.
That's
Doctor, do you like politics?
No, not even a little bit.
Me? Neither. Anybody here like politics?
I like watching it to see the circle play out.
I think that we should vote out every single politician, period, because they all have demonstrated they cannot work and play well nicely with each other. Every politician.
Yeah, but I think the people that we would like in the place will also.
I agree. But I think we should give a whole new pot of people a chance because these people have ruined theirs.
Supreme leader.
I mean, it is clear that they have demonstrated that they cannot work and play well with the others.
It's kind of designed that way.
Yeah, it's not a new problem, I agree. So again, this is just solving the equation depending on being a population proportion versus being a mean, but it's the same concept. So, I mean, we can do an example with numbers, but it's just plugging in the numbers. You want to do one? Okay. I was going to let you go, but you want to do it. I was like, I was going to let you go, so. Do you want to see one, though?
No.
Wait,
No.
You do, don't you?
I mean, I do.
Okay.
Everyone else doesn't.
it's okay.
No,
Mike,
it's fine.
It's okay. Let's do it.
All right. So let's look at 6.6-11. Why do you feel bad?
Because we kind of, that was kind of.
I shouldn't make her like feel bad for wanting to see another example.
Yeah.
I'm not trying to, I'm sorry. Let's do it. I'm excited to do this project.
Sorry for being late.
All right. So this says that at a hospital in England, only 25% of patients were using canes of the correct length. Canes, yes.
Welcome to the NHS.
Well, 2 minutes. We got
2
it.
minutes.
We're fine.
We don't have a test today, so I can keep you longer. Oopsie.
Well,
All right, so 25, this was at a hospital in England. It says, suppose you were interested in estimating the proportion of Americans who use canes of the correct length. Okay. Merca.
our healthcare system? Our healthcare system is better. Yeah, we have sorting canes.
That's true, you have sword canes. I bet England just has the liquor canes.
Yeah, they open theirs up and they use them there.
All right. They want the margin of error of 0.04. Okay, so there's two ways that you could do it. And we should see what the difference is between the two values. So again, our formula is the z sub alpha over 2 times square root of p times 1 minus p over n equals our margin of error, which in this case is 0.04. What are we definitely plugging in for z sub alpha over 2? 1.96, right? What are your two possibilities for plugging in for p? Okay, 0.25 is one possibility. Why would that, might that be a number we would use?
Because that's the biggest that it can get.
That's not why I plugged it in for p, not used it for the whole product. Why would I possibly want to use that number? Why would I possibly want to use that number? Yeah. We have an instance of where it was 25%, right? So that's one reason why we might want, that's the same reason why we use the sample standard deviation in the margin of error for the mean part, right? We had a sample that had that standard deviation, so we used it in the estimate. What's the other possibility we might try? 0.5, so that makes the numerator 0.25, right? That we use 0.25 here in the formula if we're confident that 0.25 is a decent estimate for what the population proportion might be. We have an example of that as a p-hat. This is, I want to make my margin, I want to use the maximum possible value for what p times 1 minus p could be, assuming I have absolutely no idea what p is. So I use 0.5 for p or 0.25 for the product. And then in both cases, you would solve for n. Does anybody, no one's typing in their calculator, so anyway. That's okay. We're out of time anyway.
So is it still equal to?